Welcome folks. So in this video we're going to work through an example problem that is pretty common. Here we have a gear on the left with a radius of 5 centimeters. We don't know how fast it's turning, but it's turning the smaller gear on the right. That smaller gear has a radius of 4 centimeters, and we also know that that smaller gear has an angular speed or angular velocity of 25 RPM, revolutions per minute. Question: what are the linear and angular velocities of each gear? Well, we already know, of course, the angular velocity of the smaller one. So really, the question is, find the linear velocities of each gear and the angular velocity of the one on the left. So I'm going to tackle the angular velocity first of that first gear. So I'm looking for omega 1 here. Well, we want to think back to our connections between angular and linear velocity, if possible. So remember that the linear velocity, that's v here, the linear velocity is actually just equal to r times the angular velocity, just in general. Yeah, assuming we have everything nice and figured out in radians. But that'll work out. Now, if we want to find just the angular velocity, remember that the angular velocity here is simply theta divided by t, theta over time. A problem: we have no idea how fast, or we have no idea of how long it takes to get, say, from this angle to this angle. We have no idea. So unfortunately, we're kind of stuck in terms of getting the angular velocity of that first gear. If we instead, though, look at the linear velocity. Think about this. These gears, well, pretend that they're actually, closer and they're wedged between each other. If this gear on the left is turning really fast, like a lot faster than this one is, then actually our machine here, whatever this is, maybe it's a function machine, is actually going to break it. It won't work, right? Because each of these teeth have to turn one of these teeth, and so on. And so they have to go on 1 and 1, 1 and 1, 1 and 1. They have to match up. What that essentially tells us then is that the linear velocity of the first one and the linear velocity of the second gear are actually exactly the same. Think about it this way. If these were just wheels instead of actual gears with the teeth, this is some circle here. So pretend maybe you have a car on a treadmill, or you do this on a dyno too when you're testing your car. If you have that circle and this circle, if this one's spinning counterclockwise and this one's spinning clockwise, then they would be going the same speed because one would turn the other. Okay, if that's the case, then, well, I can now rearrange this equation, because this would then let us say, this equation being this one right here, if I divide both sides by r, then actually I have the velocity the linear velocity divided by r actually gives you the angular velocity, and that I know. Excuse me. Wait, I realized I didn't actually need to do that. But, so the linear velocity of 1 is equal to the linear velocity of 2, but this is actually equal to the radius of 2 times the angular velocity of number 2. We have this information because this is, let's see, the second radius is 4 centimeters, and our angular velocity on the second one here is 25 RPM, or revolutions. Sorry, I'm getting right cursor there. Revs per minute. If I work this out, again, revolutions per minute, this is like radians, so it's the unitless. So I don't really have to worry about that. And this velocity then is just going to be 100 centimeters per minute. If I wanted to deal with it in terms of a different unit, like maybe I want to do centimeters per second, then I can adjust it accordingly, but I don't need to worry about that because in this instance I don't particularly care. Okay. Now notice that, again, this is the linear velocity of the first one, but that's also the linear velocity of the second one right here. And what's nice is that now that I know the linear velocity of that first gear, I can actually use that to find the angular velocity right here in that red box. So now the linear velocity of gear 1 divided by the radius of gear 1 will give me its angular velocity, which is, let's see, 100 centimeters per minute divided by the radius here. In this case, the radius is 5 centimeters. Comes out to, again, 20 RPMs. Right? So that's how you can use the fact that these two gears actually have the same linear velocity when they're interlocked and turning each other to find the linear velocity of the other one / the angular velocity of each gear. By the way, we should note that this answer actually does make sense because, again, they have the same linear velocity. This is the same. That means over some amount of time, these gears, like maybe over a couple seconds, they both go through 1, 2, 3 gears. Remember, the big one has more gears, assuming they're evenly spaced, right? And so it's going to make sense then that the angular velocity of the bigger gear is less because it's going to take longer to go through all of its gears and get all the way around and rotate a full 360 degrees.